If you're a business analyst who want to learn how to draw UML diagrams, this video is just for you. Unlike other courses on YouTube, this one is specialized for business analyst needs, and it covers 5 essential diagrams that every business analyst needs to know. Each section of this video will explain why do you need specific diagram, you will learn about notation elements, and you will see an example of how to build a diagram. UML use case is a behavioral diagram. It describes actions or use cases that the system can perform, working with external users or actors. By system, you should assume both process and software, as UML use case can describe business and system interaction. It is a high-level diagram, so you should not include too many details. Instead, you should use it to communicate complex, high-level ideas in a simple way. To start making use case diagram, you must define the subject. The subject of a diagram describes the boundaries of business, software system, or physical device for which you make a diagram. The subject, also called a system boundary, is a rectangle with subject's name in the top left corner. Examples of a subject could be the restaurant as a business, ATM as the combination of physical device and software, or maps as an example of mobile application. Next, you want to define actors like users and other systems that will interact with the subject. You don't have to list all separate people here, but roles. The role is a type or group of people or systems with unique needs regarding a subject. It is essential to list roles, but not separate individuals, because a single physical entity sometimes may play different roles within the system boundaries. Examples of roles are customer, payment system, or bank. There are two types of actors. Primary actors usually trigger the use case, while secondary responds within the same use case. To visually distinguish them, put primary actors on the left and secondary actors to the right. Now we should consider relationships between actors. For example, one may be a specialized form of another, like an admin or super admin. The super admin will have features of an admin role plus unique access to manage other admins. Relating one actor to another is called generalization, with an arrow pointing from child to parent. You can generalize use cases to other use cases and actors to actors, but you cannot generalize actor to use case or vice versa. Now, when you know what you are creating and for whom, you may define list of use cases. Use cases allow you to capture actions that actors should be able to perform. Those actions must have specific results. So basically, use cases are features and job responsibilities, like manage products or conduct an interview. The use case is always an ellipse with a name inside or below the ellipse. From experience, the inside is better when you start adding relationships. There are no strict use case naming policies or standards. At the same time, a common industry approach is to use verb and entity, like manage users. The practice goes deep into object-oriented programming principles, but you really don't need to dig into them. Just remember to use this approach and you are good to go. In some cases, it is allowed to use just a verb when it's clear without an entity and there is zero chance of mistake, like register or sign in, but those cases are very rare. When creating a UML use case diagram, you don't provide a detailed description for each use case. You just list them, a link to actors and each other. The description is usually created separately, later, using one of the common requirements models like plain text or use case scenarios, or one of the activity, state machine, or sequence diagrams. Use cases related to the current subject should always be located inside the rectangle, while actors should be outside the system boundary. Similar to actors, use cases can be generalized. For example, you may have different authentication approaches for the system, like username and password, socials, and one-time password. In this case, sign-in would be the parent, with all the options being children. At this step, you have all the entities, you can start linking them with 3 kinds of relationships. The first one is exclusive to link actors and use cases, and it's called association. If you have an association between them, it shows that the actor and use case somehow interact or communicate with each other. This type of relation doesn't have any direction, even though the actor is assumed to trigger use case, so you should use a plain line with no arrows on its ends. You can use multiplicity when it is necessary to show how many users of the same role interact with the use case at the same time. For example, if you need at least 2 players to play the game, add 2 above the association between the actor and the use case next to the actor's name. By the way, if you want to catch future tutorials on other UML diagrams, click the subscribe button below this video. The second and third types are exclusive to connect use cases and are called extend and include. Extend is a directed relationship that shows optional additional usage of a given use case. For example, if you want to create an account, you may go through the process immediately. But sometimes registration is a bit complicated and you must go through the help section to make it work. In this case, help with registration extend register an account feature. Extended use cases must make sense independently and may be directly associated with actors. Maybe you are one of those people who first read full instruction and only then acts. In such case, you will both extend help to registration and associate help with an actor. Include is entirely different. It is also a directed relationship, but it goes from the main use case to an additional one. Recently, I had to activate my new SIM card. After creating an account, I had to go through the additional video verification process before using my number. So in this case, video verification was included into Activate SIM card. You may ask, why not make it one use case? The answer is that sometimes use cases are too complex to keep them as one, and it is very reasonable to split them for ease of implementation or better user experience. In some cases, even multiple include use cases can be extracted from main one. An example of this scenario could be self-checkout in the store. While you'll be performing checkout as a main use case, included ones would be scan items, confirm your age if you buy some alcohol, and of course your payment. Usually, people understand the difference between extending and including quite well. At the same time, they almost always mix which arrow goes which way. For some reason, it feels unnatural that extension goes into the main use case but not vice versa, at least according to my students. To help them with this problem, I recommend remembering one connection type, for example, extension, and that it goes into the main use case. This leaves you with the binary choice of include going from the whole to its part, same as composition in UML class diagram works. A better way to do this is to understand the words. It's extend, not extended. With that, you may say that order Coke extends order pizza, thus building the road into the right direction. Now, after reviewing all the key elements, let's build a simple use case diagram together. And I'll take the restaurant example because everybody been to the restaurant. First, we define the subject or system boundaries, and of course it's our restaurant. Then we should think of actors, and typical actors are customers obviously, then a server and a chef. Customers make orders, they eat food and pay for the order. Servers, on the other hand, they are secondary actors as they receive an order being associated with the order food use case, so we put them to the right. They also have a unique use case, of course, serve food, so let's add it into the diagram as well. You can also associate the server with the payment, as it may act as a secondary actor here as well to facilitate the payment. The chef needs to cook the food to be served, but before that the chef must confirm the order. Confirmation doesn't make sense on its own without the order, so it has an include connection to order food use case. In this scenario, customer also has access to confirmation and acts as a secondary actor, as we assume that the customer will be notified if something goes wrong. If the customer brings children, they usually eat the food but they cannot order or pay for it. In this case, the child should not be generalized to parent and act as a separate actor, because child doesn't have access to parents' use cases. If customers decided to order some wine, they could of course, which would extend the food order use case. We don't put a separate association because in our context we have a restaurant but not a bar, and it is assumed that wine is usually a part of a meal. If a customer orders wine, we should also extend serving food by serving wine and eating food by drinking wine. UML class diagram is a structure diagram. In a nutshell, it represents how real-life elements translate into the blocks of code in the system. It describes types of elements known as classes, like animal or car. Classes act as templates or blueprints for creating objects, or in other words, variations of the class. Variation examples are a lion or a monkey for an animal class, and Volkswagen and BMW for a car. Each object is a unique combination of different value class attributes have, like where car color is an attribute and red or blue are values. By creating a class diagram, you map how the system would look like and basically create the first draft of a future database structure. Class diagram is one of the data modeling technique variants. The second one is ERD, or Entity Relationship Diagram, also known as a crow's-foot notation. You can use both to model on a concept level to create an independent diagram, or on a logical level to show the specific solution design, and even on a physical level to model the database. Let's begin with an overview of diagram elements. First is class, which represent a blueprint or a template for an object, defining what kind of data and behavior that object will have in a system. Think of it as a recipe for creating objects with certain properties or attributes and actions you can perform with an object or operation. Classes are always represented with nouns like car, person, or user. It tells you what kind of an object the class represents. The name should be clear and descriptive, reflecting its role and purpose within the system. Avoid ambiguous or generic names like data or object. It is a common question how to generate a list of classes to ensure that you don't lose any. There are some techniques for that. First is use case analysis. Review the use cases and identify the main nouns and actions involved into the system. The nouns are often correspond to candidate classes, while verbs suggest operations that those classes will perform, and we will talk about them later. The second technique is known as CRC cards or class responsibility collaborator. CRC cards are kind of a brainstorming technique in which you just sit and think about possible classes, their responsibilities, and who they collaborate with or other classes they interact with. Another approach is to read through all the documentation you have, specifically the glossary, and write down all the nouns that could be potential classes. You will need to filter those nouns and separate them from attributes later, and I will talk about that in the following section of this video. Attributes, also called properties, are pieces of information or data that belong to a class. They describe what an object, an instance of the class, knows or stores. Think of attributes as the characteristics or traits of an object. For example, if you have a class named car, some attributes could be color, model, or year. In the class diagram, we do not specify which color for each car, because attributes represent an object with such an attribute, but not a specific instance and value of that attribute. A lot of people confuse classes and attributes because both originate from nouns, and because a lot of people didn't have proper computer science education before working in IT, which is a common thing. To avoid confusion, best practice is using attributes for simple data types like strings, number, or dates. At the same time, if something represents a complex entity with its behavior or identity like customer or product, it should be modeled as a separate class. Remember that classes represent entities or objects that have both attributes and operations, while attributes are characteristics of those entities and usually represent simple values like numbers or text. The next category of elements is association, and there is a whole bunch of them. In general, the association is a relationship between classes that shows that classes are combined in a specific context. This line could have ands, indicating navigability, representing that you can access class B from class A, but not vice versa. I don't recommend using navigability unless the whole team really understands its value and knows how to read it. Just keep both ands with no arrowheads and you will be just fine in 99% of projects. Besides simple association, we have stronger association types for different purposes. Aggregation is a relationship between two objects, where one object, the whole, contains or it's made up of other objects, the parts. But those parts can still exist independently. For example, think of a car and its wheels. A car has wheels, but the wheels can exist without the car. The car can be destroyed, but the wheels might still be used on a different vehicle. The key point here is that the part can exist without the whole. Important to understand that aggregation, like other association types, makes sense within the context of your project, because in some other cases there might be no sense in wheels without the car and you need to use composition. The second type is composition, which is a stronger form of aggregation where the parts cannot exist independently of the whole. If the whole is destroyed, the parts are destroyed too. For example, a building and its rooms. A building has rooms, but if you demolish the building, the rooms are also destroyed. The key point here is that the part cannot exist without the whole. Finally, generalization, also known as inheritance. It shows that one class, subclass, or child is a more specific version of another class, the superclass or parent. The child class inherits properties and behaviors from the parent class, but can also have its unique features. For example, a dog class is a subclass of an animal class. A dog is an animal, so it inherits all general characteristics like breathing, but it also may have specific behaviors like barking. The key point here is that the child class inherits from the parent class. Some people mistakenly use UML class diagrams to show behaviors, like processes or actions, through associations instead of focusing on the system structure. For example, adding an association between admin and user, explaining that admin can create user. While this might be true, the UML class diagram doesn't show access to feature operations on classes, it shows relationship. So you don't need to draw such an association unless you need to keep records of which admin creates which user, which you usually don't. The confusion arises because UML class diagrams are meant to represent the static structure of a system, showing how classes relate to each other in terms of attributes and relationships, not the dynamic behaviors or interactions between objects, which are better suited for other UML diagrams like sequence diagrams or activity diagrams. There is no single bullet how to fix this behavior, it only comes with experience, so keep the problem in mind and work with your mentor. Or, if you know the universal solution, drop a comment below this video to share it with the community. Another important part of UML class diagram is multiplicity, which describes how many instances of one class can be associated with an instance of another class through relationship. Multiplicity is shown as a range with a minimum and maximum number of instances that can be associated. Multiplicity can be used for association and attributes. Let me show you example of attributes first. Single attribute value, which is default, like a person has exactly one name. Optional attribute 0 or 1. A person may or may not have a middle name. Multiple values attribute or collection. An article can have multiple authors. Also, here are some examples of multiplicities for associations. One-to-one relationship. A person has exactly one passport, while one passport may belong to one person only. One-to-many relationship. A teacher in the course can teach multiple students, but each student has only one teacher within the one course. Many-to-many relationship. Students can enroll in multiple courses, each with multiple students. One-to-fixed range relationship. Customer must have between 1 and 5 bank accounts. 0 or 1 relationship. A person may or may not have a driver's license. This is an optional kind of relationship. An interesting moment about classes, associations, and multiplicities. Remember the examples I told you a second ago, where did the article have multiple authors as a multiplicity for an attribute? This is one way to do things. Another is to have a separate author class and connect it to the article with an association. Why both are possible and valid? Because the context matters and is different from project to project. The first case works for situations when you don't need author accounts, for example, but just list of authors to choose from when creating an article. The second is for the system where authors could publish their article themselves. Before using the elements I'm going to talk about next, make sure to consult the development team of the specific class implementation. In UML class, data types help define the kind of information a class attribute or property can hold. Think of it as setting the specific rules or labels for the type of the data each attribute should contain. Here are some common data types with examples. String. Think of it as a container for text or words like names, messages, or descriptions. If you have an attribute called name with the data type string, it can hold values like Alice, hello world, or any other text. Integer. This container holds whole numbers without decimal points like counting numbers. An attribute age with the data type integer could have values like 5 or 100 but not 23.5 as it's not a whole number. Float or double. These are containers for decimal numbers used when you need to store fractions or more precise numbers like price. Boolean. This type holds true or false values, like yes or no questions. For example, if you have an attribute is active with a Boolean data type, it can only hold true, yes or false, no. Perfect for checking condition like if this account active. Finally, the date data type is used to hold information like day, month, and year in different formats. The next advanced category is operations, which represents the behavioral features of a class. Operations define what actions an object of the class can perform. Operations are typically placed in the bottom compartment of a class diagram. Operations are written in the following format. Visibility defines who can access the operation. I will talk about it explicitly in a moment. Name, showing the essence of the operation, for example, deposit or withdrawal. Parameter list, a comma-separated list of operations parameters each specified as a name. Return type, showing the data type the operation returns, which is optional if there is no return value. Now about visibility that works both for operations and attributes. Imagine that you have a collection of books and you decide who can read which book based on their access level. Here is how the main types of visibility work. First, public. Think of a book you keep on the living room table. Anyone who visits you can pick it up and read with no restrictions. In UML, such an attribute will be marked with a plus. If a class attribute is public, any other class can see and use it. Second is private. Imagine a diary you keep in your bedroom drawer. Only you can open it and read it. No one else can access it. In UML, it would be marked with a minus. Private attributes or operations can only be accessed within the same class. Next is protected. Think of a family photo album in the living room cabinet. You, your siblings, and close family members are allowed to open and see it, but not just any visitor. In UML, it should be marked with a number sign. Protected attributes and methods can be accessed by the class that created them and by any subclasses that inherit from it. Finally, package. Let's say you have a set of game instructions and keep them in the drawer in the game room. Only friends who come over to play know it's there and can use it, but people outside your home don't know it exists. In UML, such an attribute or operation has a tilde mark. Package level visibility allows access within the same package, like group of classes that are related. I assume that you might have expected more elements here like interfaces, dependencies, objects, and other elements that are a part of UML class notation. I assume that they are pretty useful and maybe system analysts use them a lot. At the same time, the majority of business analysts would never even touch them, as they are too technical. So apologies if you wanted that, but you'll have to go somewhere else to study them. The only thing I could do for you is to point you toward the resource called umldiagrams.org, which contains a lot of information about all the different diagrams and its elements. Now, let's create an example of UML class diagram.
Let's do a very simple example for online shopping. First, we need to create a list of all the classes that will be in the system. So we have obviously the customer. Customers will pay for the orders. They will make orders, obviously, so there's not a class. And yeah, they need to first browse through the products to understand what they want to buy. And actually, before they get to the payment, they first put their products into the shopping cart, I suppose. Yeah, we can add that as well. And I think we could start dealing with that actually. So we can start by adding attributes to the customer. So what would they probably have? I think we can go with a name, and of course there's gonna be a password for them. Oh, and login. Yeah, of course login should be there as well. Okay, let's do that. Maybe they'll have some ID so that we can easily find them in our system. Okay, that's probably enough. We're not doing something very complicated, going with a simple example here just to showcase how it looks like together. So next is gonna be products, right? So what's gonna be there? Product name, and of course there is price, and there is gonna be some kind of details, probably like description, so that you know what you're buying. Maybe there are more details depending on the product, but that's the basics one. Before we proceed, I need to fix this important mistake. So we don't use plural, we use singular for class names always, because every class represents the blueprint of an object. The first hunch would be to connect customer and a product, because customer buys products, they view the list of products, but that would be a huge mistake, because instead of creating relationship, we try to show behavior here, and I was talking about this in the video. So we don't add this connection. Yes, of course they can view the products in the system, but they do that through the interface, not the connection. So we don't actually have a relationship between the customer and the product in our database. At best, we have connection between customer and order, and products can be added to order. So we connect them in this way. But we added a shopping cart here, so it's gonna be a little bit complicated. So the customer adds products into the basket, into the shopping cart, before they put it to the order. Modern websites have separate classes and separate entities for shopping carts, because in this way they can email them you and remind of the purchases that you didn't finish. So yes, what you do, you put products in the shopping cart, and then when you want to check out, the system creates order based on the shopping cart you created. And of course, the customer performs payment for that order, but we also pay for the specific order. That's why we have this relationship right here. In this way, customer will have access for the products they bought through this whole connection, through this whole line. But we also need to understand that while the order is connected to payment, we also need to connect customer to the order. The reason is because when we create an order, it's relevant to one and specific customer. We cannot have the same order for many customers unless there's another system where we can do, but in our there's one customer and one order. So we add a composition here. Why a composition? Because without the customer there is no need for that specific order. So there is a very strict connection between them. The same goes for the customer and the shopping cart actually. As I mentioned before, some websites store your shopping carts on that later remind you of the purchases you wanted to make but you didn't perform them. And here is the very basic example of the class diagram that you can create.
UML Sequence is a behavior diagram that shows how classes or objects in the system interact with each other over time and the order of those actions. This diagram provides a detailed view of a specific process within the system on a low level. The popular question is why business analysts must learn sequence diagrams if they feel so similar to activity diagrams or flowcharts. The answer is that those diagrams have different focuses. The activity diagram shows a workflow and is used to model business processes and flows in the system. A sequence diagram, on the other hand, focuses on displaying how objects communicate with each other through messages and in specific sequence for a particular use case or operation. They also show how long each object is alive and what is typical time for performing each operation. The first thing to understand about sequence diagrams is that they have two dimensions. The first dimension, the vertical axis, shows time. Time flows from top to bottom in these diagrams, and events at the top occur before events lower down. The second is the horizontal axis, which shows objects and participants. This two-dimensional structure allows us to show both which objects are involved and when they interact. A lifeline represents the existence of an object during the interaction being modeled. It's drawn as a vertical dashed line under each object at the top of the diagram. When an object is created during the interaction, its lifeline starts pathway down. If an object is destroyed during the interaction, its lifeline ends with an X. Lifelines help you visualize when objects are active and when they cease to exist within a particular scenario. The activation bar, also called focus of control, shows when an object is performing an action. The length of the activation bar indicates how long an object is active or processing a message. In advanced diagrams, you will find time in milliseconds, showing the total time activation bar is alive. Now, when the canvas is set with lifelines and we understand activation bars, we can start having fun and adding call messages. The call message is depicted as an arrow pointing from the sender, the object initiating the call, to receiver, the object receiving the call. First is synchronous and asynchronous. A synchronous call requires the sender to wait until it gets a response before continuing execution. This message type is depicted with a solid arrowhead pointed from one object lifeline to another. An asynchronous call, on the other hand, allows the sender to continue without waiting for a response. This type of message is shown with an open arrowhead. For example, a synchronous call might be used when querying a database for information, but you need to wait for data before proceeding. An asynchronous call could be used when sending an email. You don't need to wait for confirmation before moving on. A return message indicates that an object has completed processing and is returning control back to another object. For instance, you'd expect a return message with the result after querying the database. Sometimes an object may need to call one of its own methods or perform some internal action. This is called a self message and is represented by an arrow looping back onto the own lifeline. If object B needs to perform some initial validation before responding to another object, it will send itself a self message. For example, if shopping cart needs to validate whether all items are still available before proceeding with checkout, it could send itself a self message indicating this internal check. A create message shows when one object creates another during an interaction. This is represented by an arrow pointing from one object's lifeline to a new lifeline. For example, in an e-commerce system, when a customer places an order, we might see a create message where the system generates a new order object. A destroy message indicates when an object is terminated during an interaction. For example, once payment has been confirmed and processed successfully, if there is no further need for temporary session data like card session, we could destroy this session using the destroy messages marked with an X. Finally, there are lost and found messages. A lost message occurs when a message leaves your system without reaching its intended destination. In contrast, a found message enters your system without any known origin, perhaps coming from some external system or user input. These are less common but useful in certain scenarios where external systems interact with your software in unpredictable ways. For example, when the system sends data out via API but doesn't receive acknowledgement from external services, this would be captured as lost communication within our sequence diagram model. Sometimes interactions include conditions or loops that require special handling in sequence diagrams. UML provides combined fragments for those scenarios. Those fragments allow you to model complex interactions like alternative paths, optional behavioral loops, and parallel actions. The out fragment represents alternative paths based on conditions. For example, if payment succeeds, one path is taken. If payment fails, another path is followed. The opt fragment shows optional behavior that only happens if certain conditions are met. This is useful for modeling features that may not always be executed depending on user input or system state. For example, if the customer applies a discount code during checkout, we can use an opt fragment to show this optional behavior. If no discount code is applied, the interaction part is skipped. The loop fragment represents actions that repeat multiple times. This is useful for modeling iterative processes within your system. For example, adding multiple items to the cart would be represented using a loop fragment, since this action can occur repeatedly until checkout. The parallel fragment allows parallel execution of actions, which is useful when multiple tasks happen simultaneously. For example, if inventory updates and payment processing happen simultaneously during checkout, we could use a par fragment to represent these parallel actions. Now that we've covered all the elements in detail, let's create an example of UML sequence diagram. For this video, I selected a typical example of online shopping experience. To model this shopping experience, you will need the following lifelines or elements in the diagram. The first element is user or customer, the person who enters website and buys stuff. The second is a login module. It's not mandatory since you can buy stuff even without your account. At the same time, this is a typical feature and I would like to show you how it works in sequence diagram. The next thing is product catalog. In our case, this lifeline represents all the features related to searching and viewing products. The next one is shopping cart, which is self-explanatory, and checkout and payment. The reason I have two lifelines and they are not together is because payments in this case is a third-party solution. We begin modeling from the moment when the user tries entering the system. For that, user enters their credentials and system validates them. This is where we can use our first known combined fragment, which is called alternative. It represents two different variations of the same flow depending on successful or unsuccessful credentials validation. In case of successful validation, system asks user to provide an OTP, one-time password, and validates that OTP, and if everything's okay, we return user to the logged in page. In this diagram, I skipped two moments. First is the interaction between the login feature and some third-party solution that requests an OTP for the user. In this case, this will overcomplicate the diagram, so we just assume it happens. Another moment is OTP validation. Basically, I need to add another alternative here showing what happens if OTP is not validated successfully. But for the sake of your time, I skip that point and we just return user to the logged in page in successful validation case. If credential validation failed, we return failed message and user can try again. After we get into the system, we get to the loop combined fragment. Basically, the flow in which user search for the products, system fetches products and returns the list of them to the user. User selects and views some product and system shows the product details. To make things more interesting, I will throw in an optional combined fragment to show that adding product to cart and receiving successful adding message is completely optional. User don't have to do that. At the same time, in this diagram, we assume that the user will do that because we will continue with shopping cart and checkout. After our user added all the products they wanted into the cart, they need to review it. To do that, they request the shopping cart and it returns its content. We assume that our clients may modify their shopping cart when they review it. That's why we throw in this optional combined fragment as well. We could have used a loop here as well, but it will overcomplicate the diagram because the loop happens for the same optional combined fragment, for the same elements. That's why I skipped the loop here and the next step is proceeding to checkout. During the final steps, the system returns the checkout form. User enters their shipping and billing information, system saves it, and basically returns the message that the information is saved. After that, the user enters their credit card information and pays. Our system sends payment request to the payment agent, which validates the credit card information, and if everything's successful, it charges the credit card. Then the system returns the success payment message, which our system shows to the user after redirecting them back to products page. UML State Machine, or just a state diagram, is a behavioral diagram. It shows the different state of an object or a system, how they move from one state to another, and what triggers those changes. This diagram is helpful for many stakeholders. For example, developers would see a list of entity statuses and what makes them change. Designers, on the other hand, could get some ideas too, assuming that each state is an end screen and triggers are users' actions, while the whole diagram is a user flow within the system. To create a diagram, we first need to consider a topic. I suggest we create a state machine diagram for an ATM, something we all use often. The first step to building a diagram for this process is considering all possible states. What could be the state for the ATM in our case? Let's drag a bunch of simple states out there. When we approach the ATM, it's obviously idle and waiting. Then we insert our card and it becomes operational while we use it. Sometimes when we approach the ATM, it is out of service or even off, which is a bummer, of course. We could also assume that at some point each ATM needs to perform self-diagnostics and send information to the server. Or we could even see the technician working on fixing something, meaning there should be some kind of maintenance mode. Cool, now we have all the major states we could think of, and now we can start charting transitions. But before that, we need to add an initial pseudostate. In the beginning there was nothing, meaning the ATM was off. Then someone, probably a technician, switched it on. It is wise to perform self-diagnostics on the startup, so let's put a transition here as well. If everything goes right, the ATM should get into an idle state and wait for the customer. If not, it would probably go straight to out of service state. When the customer approaches the ATM, they insert their card and, considering the ATM is working, they make it operational. Looks good, but at this point I start seeing that the operational state is too primitive and doesn't show a lot of stuff that the user or ATM does. So let's throw some details into that. For that, we can use the composite state. Basically, we expand the state and add a bunch of substates inside, where we can add all the screens the user goes through. First is customer authentication, which includes entering your PIN code and verifying the card by ATM. What you can do here is to combine them into a single state, not to bother too much, or create them separately, or even develop more states to show more different steps. I feel kind of lazy today, but intelligent lazy. What I will do is to call it customer authentication and mark it as a hidden decomposition composite state by adding this symbol, assuming that there are more steps inside, but I will work them out later. Looking good. Next, what we do is to choose an operation. We can have many different screens here, but it's not that important to mark them all, so let's make another composite state. Now, when we choose an operation, which is usually getting some money, we can start performing our transaction, which is also a complex process. So for the sake of your time, let's not dive too deep into it. Adding those three steps shows how we use the system as customers. So now we can add a final pseudostate and roll with it. If everything goes right during the operation, the system should return to the idle state and wait for another customer. But what if there is a problem? For example, we can enter the wrong amount and want to change it, or we entitled to change our mind completely because now for some reason we don't need any money. In this case, we can cancel everything and the system returns to the idle state using an exit point pseudostate because it's an exception path. What also could happen is a system failure, like money chewed within the ATM. In this state, the system cancels the operation but cannot return to idle due to an error. In this case, the system should go to the out-of-service state through another exit pseudostate. When such an unfortunate thing happens, someone should call the technician and put the system into the maintenance mode until they fix it. Sometimes ATMs cannot be fixed at all, it's a bummer, and the maintenance fails. In this case, the system might be sent back to out of order until fixed or switched off to be removed completely. To finish the list of possible transitions for this diagram, we should also mention that the system might require some kind of planned maintenance. Thus, we should add another transition from idle to maintenance. Or we might need to move completely functioning ATM to another location, so we need to switch it off, adding another transition to our diagram.
Let's begin with an overview of diagram elements and nodes. There are four groups here: action edges, actions, controls, and objects. Actions or action nodes are named elements that represent a single step within an activity. It is important to keep all actions on the same level of abstraction within the same diagram. For example, your diagrams contain major steps like create order, confirm order, and send order. This means that if you want to add another step, collect order, you should not decompose it into smaller steps like go to post office, verify ID, and others, but keep it as collect order. Actions are round-cornered rectangles. The name or description of an action is placed inside the rectangle. To name an action, use an action verb or noun for that action that is concise and clear. Some action name examples are enroll a course, upload file, and checkout. Actions have several types that are useful in different cases, but majority of them add complexity to most of projects. That's why, beside default actions, today I will cover invocation send signal, event accept signal, and event wait time. The first two work in pairs and show asynchronous behavior similar to BPMN message flows, when an action shoots a message and doesn't wait for the response to continue the flow. An example of a send signal is to notify customers when the status changes when an order arrives at the post office. An example of an accept signal is when this message triggers collect order action. There is also wait time action. It works like a timer event in BPMN. It triggers an action by the schedule repeatedly or after waiting for some time. For example, check the order status every hour and send updates. The second group is action edges, arrows that connect different nodes, but mostly connect actions. The most common are simple arrows showing what is the next step. Sometimes, to show the default flow, if you have many of them, you can use the default action edge, which is the same arrow but with a dash on it. There is also an interrupting edge. It shows when we need to leave some part of activity, called an interruptible region, to jump into another part of an activity, like canceling an order after creating but before its fulfillment. Action edges always stay within a single activity. You cannot use them to connect multiple activities or connect actions from different activities. So, unless you use specialized UML software, you don't need that, as you can just put together a document listing all activities and connections. But if you really need to connect that graphically for some reason, either use annotations or call behavior actions. If an edge goes into action, it is called an incoming edge, and if it goes out of activity, an outgoing edge. The next group of elements is controls or control nodes, coordinating the flows between other nodes. There are several types of control nodes, and the first is an initial node, where the flow starts. Activities may have more than one initial node. In this case, we assume that all initial nodes are triggered at the same time and start multiple flows that could connect. Note that flows can begin with other nodes, so initial nodes are not required. At the same time, they visually help you find the first step, so I suggest you keep them. The second is a pair of final nodes. Flow final nodes and all tokens that arrive at this node but do not affect other flows in the activity. And there could be multiple final nodes. On the other hand, an end node is always single, as it depicts the end of flows in the whole activity. Next is a fork join pair, which is responsible for splitting a flow with a fork node into parallel flows. They could proceed in parallel or might merge through the join element. For example, when the company receives an order, you can use the fork to show that the send confirmation and prepare order can happen at the same time. Before shipping an order, you need to perform both, so you join them. The final pair is a decision and merge nodes. A decision node is a control node that accepts an incoming edge and selects one of the multiple outgoing edges. The goal of decision nodes is to support conditionals in activities. Each outgoing edge should contain exclusive conditions represented by a text node called cards, and be evaluated to decide which flow to choose. The order in which to draw flows is not important. At the same time, to make reading the diagram easier, either put flows on priority from top to bottom or use the default action edge. Merge node brings together multiple incoming alternate flows to accept single outgoing flow. Merge should not be used to synchronize concurrent flows. For example, if a decision is used after fork, the two flows coming out of the decision need to be merged into one before going to a join. Otherwise, the join will wait for both flows, only one of which will arrive.
Remember, decision nodes work same as with BPMN, meaning that there is always an action that precedes and defines the decision, while the node just contains conditions and decisions. The final node's category is objects, representing actual objects passed between actions. In my experience, everybody understands that when a diagram has a create order and process order actions, it is assumed that the order object is created during the first action and is passed to the next one. Because it is obvious 99% of the time, in most cases there is no need to use this category. Since most projects don't require such details, I will limit our object discussion with this brief overview. When you combine all elements, you get an activity. You can either leave it outside of container or add a round cornered rectangle with the activity name in the upper left corner and add nodes and edges of the activity inside the border. This helps to visually understand the scope of activity. With that, your simple activity diagram is basically done, but sometimes it's not just enough. What else you could do is to use sub-activities. Basically, this means decomposing some action within your diagram into separate activity with all the relevant nodes. Just remember that sub-activity cannot leave its boundaries through action edges and does that through the activity and node only. Sub-activity can have call behavior actions though. Another way to add details is to throw in swim lanes that show how activity is performed by multiple actors or users. It is a useful way to show who is responsible for each action within the same process. You can also add loops to your workflow. To create a loop, make a simple flow with actions and decision node like open message list, check if new messages are available, and if yes, read one, get back to the list, check again, and if no messages are left, and activity. The final piece of advice before we jump to an example is how to draw the whole activity. It doesn't matter whether you go top to bottom or left to right, both are fine. Just don't draw them from the bottom to top. As for the cultures using right to left writing, they still use the same left to right approach or top bottom approach. Now, let's create an example of a UML activity diagram. We begin with initial node to kick off the diagram. Every shopper starts by searching for products in one of three major ways. First is by searching for specific products and then browsing search results. Second one is by going to deals section directly. And the third one, probably the most popular, is browsing categories and then a list of products from that category. In any of those cases, the client will get to the product's details page to view the product. After the product review, they will either go back to search or put the product into the shopping cart. Here is where the choice happens. Either continue shopping, go back to search, or it's time to check out. Before checkout, it's time to review the cart, place an order and pay. We might call it a day, but I want to go one step further and show how other elements work. Let's move up from the specific user flow to the whole business process and see this activity as a part of the process. In this case, our previous activity becomes sub-activity, and we add another initial node to kick off the whole process. The activity that we created becomes the first step, the first action, and then we go to processing, shipping, and closing the order. We should also recognize that during processing, there is a chance that the order will be cancelled. Because of that, we need to add interrupting region and an event that requests the cancellation. And of course, the subsequent activity to process this cancellation. Also, after the shipping but before the closing, there is a chance that the client will return the product. Knowing that, we need to add a window of, for example, 30 days and add a time event showing that after 30 days we should close the order. But before that, we add another interrupting region and show that the order could be returned, and then we need to process it again. And that's everything that you need to know about UML to cover 99% of your business analyst tasks. If you enjoyed this course, subscribe to my channel to catch more courses in future.